if you turn this video off, then please tell me the reason why, so that I can improve. Otherwise, hi, welcome. I'm trying to learn particle physics today. How the Higgs was found, or the Higgs boson. And after we've done it, we're going to do standing yoga. If you participate in the standing yoga, then it's very risk. Quarks also have a separate colored charge onto which particles known as gluons latch to produce a strong nuclear force. So the electromagnetism is between the free quarks inside of the protons. And that is the electromagnetism. And now we're having the gluons, they are making a strong nuclear force. This force is indeed much stronger than the electromagnetic force, so electromagnetic force, but peculiarly, gluons themselves carry color charge and so stick to each other. So the gluons themselves are sticking to other gluons. Consequently, quarks and gluons are never seen roaming freely, but only ever bound inside particles such as protons and neutrons. And the strong force never breaks out beyond subatomic scales. We're saying these quarks and gluons are never outside of protons, because they're put together. As for the third of the Standard Model's forces, the weak nuclear force, it is weak, but without it the radioactive decay that powers the Sun and other stars would not occur. Its weakness comes about because its carriers, the W and Z bosons, have very large masses, almost 100 times the mass of a proton. Okay, the weak nuclear force, it is weak, but it is the thing that makes radioactivity in the Sun possible. Because the W and Z bosons, they are 100 times more heavy or have more mass than the whole proton. Creating such particles takes a lot of energy. Under normal conditions, matter particles prefer to interact by swapping massless photons, if they can. Okay, if it's normally it's just happening the electromagnetism with the photons. Photons are massless. Photons are light, basically. Light is a part of the electromagnetism. Photons are massless and they can just do electromagnetism. That's easier. But it is also possible that this radioactive thing which makes radioactivity possible happens with the W and Z bosons, which are 100 times heavier than the whole proton. At very high energies, in the first split second of the universe, for example, or in collisions in powerful particle accelerations, this difference melts away. Okay, if the energy is very high, for example, if two atoms collide together, then there is no big difference between the easy happening electromagnetism, which is carried by the photons, and they are massless, so it's just easy to move them from one place to another one, because they don't weigh anything. But equally easy to do the weak nuclear force, because they are now at high energies, not 100 times more, or it doesn't matter, than the fragments of W and Z boson, which are doing the weak nuclear force. The electromagnetic and weak forces, so hugely different in our everyday experience, become one unified electroweak force. Okay, at high energies, at the beginning of the universe, or in these large hadron colliders where we're banging two atoms together, at these situations, the electromagnetism and the weak nuclear force are becoming together the electroweak force. They are now equally easy to have, for some reason. The process by which the electroweak force splits into the electromagnetic and weak forces is known as electroweak symmetry breaking and must have happened sometime in the universe's early moments. So, after the Big Bang, they say there was not enough energy, high energy, and it again mattered that weak nuclear force has to be transported with a transporter which is 100 times as heavy as a proton, whereas the other has one which weighs nothing. Whatever caused It is whatever caused it is early connected to the mystery of mass. Okay, they try to understand why things have. Why do things at all have mass? And they're saying here that it is a mystery, basically. Why do things have mass? Why does this book basically take? Not because of gravity, but why is gravity existing? And gravity exists because because this book has a mass and is pulled on by another object with more mass. And they're saying it's a mystery, where does mass come from? And they're saying after this high energy is away, again the electroweak force plays a part in it, and now it doesn't work anymore. Now it's again heavier. The electroweak force doesn't work. After all, it is the mechanism by which the W and Z boson acquired mass. Okay, directly after the Big Bang, the W and Z boson acquired mass. The Higgs boson was initially postulated to explain just how the symmetry came to be broken. In the moment of the Big Bang, all when two things collide, two atoms, then there is electroweak force. Because at that moment it is for the particles the same easy to do electromagnetism. I don't really know what it is now doing. It holds the things together, but it's strong. It holds the things together. But the photons as doing the other force, the weak nuclear force. And the reason why this electroweak force isn't present in the universe, the idea was to explain it with the Higgs boson. This chapter is about the Higgs boson. But it seems a bit more as if it were the W and Z boson. Broken symmetries aren't restricted to exotic forces. An everyday example is seen when a liquid cools into a solid crystal. Here, a broadly symmetrical state, everything looks the same in all directions in the liquid, is replaced by a state in which things look distinctly different along different axes. I don't really know what they're talking about. I think they mean, or we can just take another example. We're having a puddle of water and there's all flat. As soon as the ice crystals come, it isn't. Ice, perfectly clear ice is perfectly clear. That is very perfectly clear. What do we say? When a liquid cools into a solid crystal, a broadly symmetrical state, everything looks the same in all directions in the liquid, is replaced by a state in which things look distinctly different along different axes. And an ice block looks a little bit different. Let's just take better, this enough. Ice looks a little bit different than water, does it? Yes, it does, but does it just because there are some, what is it called, some things in which should not be in it. So, as I said, ice can be completely, not as a crystal, big like a snowflake, you can't look through snow, but there can be very, very clear ice, frozen ice. But yeah, that was just an example. In the 1960s, particle theorists began to wonder whether tools developed to describe the symmetry breaking could be applied to the cooling cosmos. Okay, the symmetry breaking. That this high energy is not present anymore as it was with the Big Bang, and not the symmetry out of weak force. W and Z boson easy doing it because of high energy, and the electromagnetism easy working because of a massless photon is not anymore, and the electromagnetism is still very easy because the photons are still massless, and the very heavy W and Z boson. And then it's not the idea, they are already 100 times more heavy than a proton. What if they're getting 101, 102, 103, 1,000 times more heavy? Is that the reason why the universe cools down? This was no easy task. Molecular interactions in a solid or liquid can be defined by reference to a fixed set of coordinates. But thanks to the warping of Albert Einstein's general relativity, there is no such standard frame or reference for the universe. Anyway. In 1964, theorists Robert Broad and François Englot devised the equations of a quantum field that would pervade the cosmos and break electroweak symmetry while being consistent with relativity. Okay, they made a formula, an equation, and saying this is how it works, even that there is no symmetry anymore between electromagnetism and weak nuclear force. Physicist Peter Higgs made the same proposal and pointed out that the ripples in this field would take the form of new particles. Later that same year, Gerard Goralnik, Carl Hagen and Tom Keeble combined these ideas into a more realistic theory that was the precursor to the Standard Model. The central point about what came to be known as the Higgs field is that even the lowest energy state of space isn't empty. So even there's nothing, there is something. Energy. It is not empty. Particles traveling through space interact with the field to different degrees, and this creates a sticky quality to the movement, mass. So the particles just in the universe are interacting with the field which is not empty, and that gives them a force, and that gives them mass. The W and Z boson acquire mass by one kind of interaction with this field, but fermions do so by another. Because the Higgs field has no net electric or color charge, photons and gluons don't interact with it at all and so remain massless. So it's the Higgs field. And the Higgs field itself has no electric or color charge, and so the photons and also the gluons don't interact with it. And that is why also gluons probably are massless. This was a neat trick. To find out if it was anything more, we needed to expose the field by making it wobble, those wobbles being observed as Higgs bosons. Theoretically and experimental developments gave us a good idea of the energy required. The Higgs boson's mass had to be between about 100 to 400 gigaelectronvolts. We would need a true huge machine. The Large Hadron Collider at CERN near Geneva, Switzerland, is housed in a 27-kilometer long tunnel. It is commonly described as a ring, but actually more like an octagon with rounded corners. In the straight sections, intense electromagnetic fields kick two counter-circulating beams of protons every time they come past, increasing the speed. By the time of collision, they have reached 99.99991% of the speed of light. Bending such a fast-moving beam of particles requires very powerful magnets. Any power lost to electrical resistance would be a brake on performance, and so magnets are made of supercooled superconducting materials. Even then, they can only achieve gentle curving. Hence the LHC's vast size. Okay, that was the particle physics part. In the next part, we're going to reread the last half page and try to understand it a bit better. But for now, that was it. If you stay here and participate in the standing yoga, we just have 2 minutes. Then it's with your arms. Feet are together, and we're starting with a sprouting flower. Breathe in and out. Out and out. In and out. In and out. Out and out to the side. In and out. Out to the other side. In and out. Make an inch space between the feet and out to the side. In and out. Out to the toes. And out and sink down a bit into the knees. Stay on tiptoes. In and up. Out to the other side. Just heels down. In and up. Heels up. Out and down. In and up. Reach high. And out we're going down. Breathe in, bend your right leg. Breathe out, stretch your left leg. In and change. Out, stretch your right one. In at the middle. Out and down. Breathe in, lift the right hand up to the sky. Breathe out, bend the left knee, look over the right shoulder to the right hand. In and down. Out and down. Breathe in, lift the left hand up. Breathe out, look over the left shoulder to the left hand. In and down. Out and down. Breathe in, come halfway up with a straight back. Out and down. In halfway up, straight back. Out and down. Breathe in, the arms again. And lean back through the shoulder blades together. In and up. Intertwine the fingers, reach high. Breathe out, reach in front, hold the back. In and up. Out across the other way around. Breathe in, reach high. Out, reach in front, hold the back. In and up. Out, lean back. In and up. Out and back. In and up. feel the hands up. Out and down. In and up. Hands together and lower them down to heart center. Now it was a short senor, but I thank you very much and next.